Right, this is 2016 number 3. It's almost like a little conservation of mass problem. They give you a bunch of stuff at the beginning. I'm gonna start by putting the equation down on a piece of paper so I can mark up masses as I go with this thing. So this is we got some M. We're mixing some I with it. When you put it in water, those two react and form this Mi2, except there's some excess metal that's sitting around at the end. That's what it says. And then it gives you all these experimental steps. Nothing in the beaker, you added the metal, you added the iodine, you added the water, stirred this guy around. The Mi reacts and forms an aqueous solution, so it's in solution, and then you got excess leftover metal. That solution you then take and put it in a test tube, then you heat it and evaporate all the water off and leave just the Mi2 behind. So we have these masses that we're going to come up with from this data chart that they give us down here. And then they ask us some questions about it. So here we go. A says, given that the metal M is in excess, calculate the number of moles of iodine that reacted. So we need to figure out the moles of iodine that reacted. We can find that based off the number of grams of iodine we have. Easy enough. This is grams to moles. This is as simple as a stoic problem will get for us. So 1A, this was the all of it together. We subtract off the metal and the mass of the beaker. So we got 127. So let me squeeze this in here. We got 127.57 grams minus the 126.549. Carrier sig figs. These are 3 digits past the decimal. When we subtract, we should have 3 digits past the decimal when we get this answer out, which is 1.021 grams of this iodine that we started with. They want the number of moles of it. So grams of iodine to moles of iodine. We got to come up with the molar mass here. It's 253.8 grams is what I got per 1 mole. And we can calculate that, and we come up with, I'm going to put in scientific notation, 4.023. That had 4 sig figs. This technically has 4 sig figs. Times 10 to the negative third moles of iodine. That's the answer to part A. That's it. Just find the moles of it. Just take your time. Make sure you're subtracting the right things up in the chart to get your numbers taken care of. Then it says calculate the molar mass of the unknown metal. So we need to calculate the molar mass of the unknown metal. And I think there's lots of different ways to do this. I know the overall mass of the Mi2, the 1.284. So that's how many grams I have of that. I just figured out how many grams of iodine I have here. I have 1.021 grams of iodine. And so there are my masses. Stop bobbing, camera. So there are my masses of those two things, which means I also know the mass of the metal here at the end of this if I subtract those two off. So 1.284, forgive me, I'm doing it on a calculator right now, 1.284 minus the 1.021 gives me 0.263 grams of my M. I want grams per mole, so if I can figure out, I got the grams, I can figure out how many moles of the M I have, then I'm in great shape. And so for part B here, I'm going to take the 0.263 grams of M, and I'm going to divide it by the number of moles of M to find grams per mole, to find the molar mass. Here's the beauty. That moles of iodine, if that's how many moles of iodine I used, then that's also the amount of M that I used, because this is a 1-to-1 ratio in this thing. And so when I do that 1-to-1 ratio, that means if I take this and divide it by 4.023 times 10 to the negative third, it's going to give me the grams of it per the moles of it. And that guy should equal 65.36. Hopefully that makes sense to us. Look, is that the amount of M that we had in the original solution? No, we have excess M, right? At the end of this, there's leftover M, but we started with 1 point something grams of M here. And so that 0.263 grams is how much reacted in that equation to make up that total amount of product. So that's the idea here. You can find that amount of M that reacted. So it's 65.36. That is our molar mass. That's grams per mole of metal M. That's B. Part C, the student hypothesizes that the compound formed in the synthesis reaction is ionic. Propose an experimental test the student could perform that could use to support the hypothesis. Explain the results of the test would support the hypothesis if the substance was ionic. This is a conductivity lab. This is one of those where we take an ionic compounds, and you can even write ionic compounds don't conduct electricity in a solid state. But we could dissolve the Mi2 and it would conduct electricity when aqueous if it's ionic. That's it. It's conductivity lab. We did conductivity lab in pre-AP. We had some light bulbs sticking on probes. We stuck them into different solutions. Ionic solutions conduct electricity in aqueous state because they've dissociated, right? They've turned into individual ions. You now have these individual ions floating around, charged particles floating around. Means conductivity. And then the last little piece of this one, part D, and the truth is there is a part E and F on this equation, on this question, but they deal with electrochem, so we're skipping them for the time being. So part D here says the student hypothesized that bromine will react with M more vigorously than iodine did because bromine is a liquid at room temperature. Explain why iodine is a solid at room temperature, whereas bromine is a liquid at room temperature. Explanation should include strengths of intermolecular types and strengths of intermolecular forces present in each substance. So we're looking at bromine and iodine. You got to talk about both of them. Bromine and iodine are both nonpolar molecules. So they only have dispersion or London dispersion forces. Period. Iodine's dispersion forces are greater because they have more electrons and therefore more polarizability. Count them, 7 syllables. My rap album, polarizability. Let's say more polarizability. That's the answer, right? Now, I would say causing it to be a solid, this causes iodine to be solid and bromine to be liquid. That's how I would write it. That's more writing than I like, but 2 sentences, 2.5 sentences. Good? Bromine and iodine, both nonpolar molecules. They only have dispersion forces. Talk about their intermolecular forces. Iodine's dispersion forces are greater. Why are they greater? Because they have more electrons and more polarizability. That's it. That last sentence probably don't even need. Good? There it is, 2016, number 3.